Very good.
Okay, hello everybody. It's a great pleasure to see that we have a full house once again in our series. And I would like to take the first 1 or 2 minutes and explain the new format that we like to keep the session in the near future. So the basic idea of the laws of nature series is to get our different scientific communities a little bit together, be it that you are from philosophy or from physics or from mathematics. And the basic idea how we would like to change the format now is that all the new sessions will give a little perspective that is targeted to a mixed audience and somehow introduce a little bit the research topic, let's say the vision, the long-term or mid-term goals, and where it's situated, and so on and so forth. And after that, of course, a core talk. So the core talk will always be, let's say, 40, 50 minutes. I mean, all these time estimates, as you know, in the Law of Nature series, are rough estimates. They are a guide, but not a rule, because we really like to have, a nice presentation, also a nice discussion in the very end. Yeah. I mean, needless to say that this is quite challenging for the speakers to address also a mixed audience. So we are very happy and honored that Jürg accepted the challenge for a first talk like that. And so Paula will say a bit more detail about the talk right now because she will take over the chair. However, this format will be roughly 90 minutes, yeah, with a 30 minutes perspective. Yeah. So
That's
Jürg,
okay.
thank you so much that you agreed to do this. And we hope that with your good example, we can attract maybe also some other people from mathematical physics, theoretical physics, or from topics where it's a bit harder to address because of the technicalities and so on to address a mixed audience. Yeah. Okay, I think I stole more than 2, 3 minutes. That's why I will stop now. And Paula, I would like to hand over to you to be our chair for today's session and start it.
Okay, thank you, Dirk. Thank you everybody for coming. And thank you very much, Jürg, for coming. So I'm happy to announce our speaker of today, Jürg Fröhlich. Before I really introduce Jürg, I want to just say that today we have this 30 minutes general introduction, which is perspectives and we would like to break after that for 5 minutes break and questions also. And then we will start the specialized talk with the longer question session afterwards. Okay, so I will try to handle that. And yeah, as I said, I'm happy that today's speaker is Jürg Fröhlich. He's from Zurich. He's professor for physics and mathematics at the ETH Zurich, where he's been teaching for a long time now. And he's famous for several papers on mathematical physics, in particular statistical physics and quantum field theories and several other things. So I'm happy that you come here today and that we can listen to your talk. Please go ahead.
So I will now share my screen. Hopefully it will work. I think it does. Share. Good. Can you see it?
Yes, perfect.
Very good. All right. So I'm going to talk about various ideas about quantum mechanics. Some of them I already talked about some time ago in the same series. I thank the organizers for inviting me once more to present somewhat more specific results today, but I will start now with a general introduction that should be accessible to just about everybody, I hope. So, here is a list of contents. So I will start with a general introduction to the problems of quantum mechanics. I will then sketch what I call the ETH approach to quantum mechanics. E stands for events, T for trees, and H for histories. This is technically easy, but conceptually not entirely trivial. Then in part 2, I will present more specific results. I will start by introducing a certain family of models of matter interacting with the quantized electromagnetic field. Then I will, in order to sort of tune your brains to the right wavelength, I will talk a little bit about diffusion and the theory of simple random walks on a lattice. Then the main section, the sort of crucial section of the entire presentation will be section 5, limb-blood dynamics and quantum Poisson jump processes. This will be somewhat technical. And if I have time, I will give a sort of special simple case of this in section 6. In any way, in 5 and 6 are really have something to do with the theory of fluorescence of atoms. And then in section 7, I will conclude. I have worked on problems of quantum mechanics basically ever since I retired in 2011 with various different colleagues and collaborators that are listed here. And again, I thank the organizers of the series for the opportunity to present these ideas. To start with, let me quote Dirac, who said, rather many years ago, "It seems clear that the present quantum mechanics is not in its final form." This statement is still valid nowadays, as far as I can tell. So here is a little summary of the talk. The talk is about the foundations of quantum theory, which is a thorny subject haunted by controversy and confusion, not to make more critical or impolite comments on what's happening in this community. I will start by trying to describe some of the key problems and facts encountered in the foundations of quantum mechanics. The main purpose, however, will be to give a brief survey of what we have tried to do, namely to find a sort of plausible completion of quantum mechanics that might invalidate Dirac's impression. Now, this will involve looking for a general nonlinear stochastic law of dynamics or evolution for non-relativistic quantum mechanics. I have chosen to leave out the relativistic case because that would be too much for a single talk. And I will try to derive my law of dynamics from basic principles, and it will supersede Schrödinger evolution. And then I will present some recent applications of this law. Concretely, I will apply the general results to problems in quantum optics, the quantum mechanical time evolution of physical systems consisting of charged matter interacting with the quantized electromagnetic field will be seen to be nonlinear, dissipative, and stochastic, featuring isolated random events, sometimes called quantum jumps. Explicit results are presented for an idealized description of such systems that arises in a limiting regime where the velocity of light tends to infinity. The equations for the time evolution involve a type of stochastic process which I call quantum Poisson jump process. Similar processes appear in the literature, but my impression is that they never quite appear for the right reasons. So I will try to sort of improve on that. All right. So let's start with the introduction. I take it for granted that the audience is familiar with textbook quantum mechanics, at least at the sort of introductory level. So suppose S is a physical system to be described quantum mechanically. Then we describe the pure states of the system by unit rays in a Hilbert space and mixed states by density matrices acting on that Hilbert space. Physical quantities characteristic of the system are represented by certain self-adjoint operators acting on the Hilbert space. The time evolution of states of the system is described by Schrödinger von Neumann evolution, and then people say, except when a physical quantity of S is measured, when you do an experiment. The effect of a measurement of a physical quantity on the state of the system is described by postulates due to von Neumann and Lüders in the conventional narrative. Namely, there is first a transition of the state of S to a mixed state, followed by state reduction or wave function collapse. And the state you collapse to has a probability that is governed by Born's rule. The Schrödinger von Neumann equation for the evolution of states is a linear deterministic equation. The only information it contains concerns spectral properties of the Hamiltonian of the system that generates this time evolution, which is really not much. Yet experiments, all experiments I can think of, tell us that quantum mechanics is fundamentally probabilistic. And this, of course, leads to this infamous measurement problem. The measurement problem has motivated the postulates proposed by von Neumann and Lüders, which, however, in my opinion, cover up a lack of theory-intrinsic understanding of measurement processes as physical processes, and they appear to lead to serious difficulties. For example, it is posited that independently of the state in which the system has been prepared, measurements of arbitrary physical quantities of the system can be carried out at arbitrary times and arbitrarily quickly, which actually would lead to infinitely large energy fluctuations, and without including the measurement equipment in the quantum mechanical description. This leads to the observation that observers play a fundamental role. All this strikes me as somewhat absurd, and we have to improve on it. These defects of textbook quantum mechanics are more or less well known, and they have been debated and discussed for nearly 100 years, but how to cure them remains very controversial. This is the problem of what people call the interpretations of quantum mechanics, among which I mentioned different versions of the Copenhagen interpretation, Everett's many worlds interpretation, relational quantum mechanics, whatever this may be, cubism, Bohmian, and finally Bohmian mechanics. Bohmian mechanics is, I think, maybe among the more serious so-called interpretations, but it doesn't satisfy me. So I will sketch an alternative, which I call the ETH-approach for you. All right, so in fact, maybe a following remark is appropriate. I think people have been concerned too much with interpretations of quantum mechanics and have not realized that we don't quite know what quantum mechanics is, and that we actually have to complete the theory so as to come up with a consistent, coherent description of nature. To begin with, the following claims will be explained on examples. First, quantum mechanics is intrinsically probabilistic. The root of this probabilistic nature of quantum mechanics is found in fields that describe massless modes, in particular in the electromagnetic field. This is a physical insight which many people are not happy with, but which I think is actually a fundamental insight, and I will try to explain how this comes about. Point two, time evolution of individual systems rather than of ensembles is not described by the Schrödinger von Neumann equation, and thus we have to search for a law of dynamics in quantum mechanics that describes the evolution of states of individual systems, and it will turn out that this dynamics is nonlinear and stochastic. This will become apparent in section 2 when I will sketch the ETH approach for you, and then more precisely in part 2, section 5. But that's going to be in the technical part of the talk. So, Point 3, to find a general law of dynamics in quantum mechanics, we have to introduce first appropriate notions of potentialities or potential events. I think the notion of events is crucial for actually just about every physical theory. In classical mechanics, it was already used. There it was simply a point in physical space or in phase space. And then we have to also clarify what we mean by actual events or actualities. Point 2, a dichotomy. We have to introduce a dichotomy between past and future, quite in the sense of Aristotle, which will lead to a fundamental arrow of time in the evolution of the world. And we will have to identify a fundamental mechanism of dissipation that sort of underlies the arrow of time. And as I already said, the electromagnetic field or other fields with massless modes appear to play a fundamental role in this. And third point, we have to introduce an appropriate notion of states. Now, as Heisenberg intuited, the time evolution of states in quantum mechanics appears to distinguish between past and future. The past is factual, and the future consists of potentialities. They are separated by the present, in which certain potentialities actualize. The theory has to tell us something about which potentialities actualize, because I would not like to introduce free will that tells us we can measure whatever we like. So we have to incorporate these points into quantum mechanics. Now, physics is primarily a science enabling one to make predictions concerning the future. States should serve to make such predictions. Thus, states should be viewed as mathematical devices enabling one to make predictions about the likelihood of certain future potentialities to actualize. I will try to take this into account when I introduce my notion of states. So let's go through these points. Item 1 was about the probabilistic nature of quantum mechanics. There is a fact. In general, one can only predict probabilities of different outcomes of experiments or observations or measurements. Let's look at an example. The Stern-Gerlach experiment for silver atoms, which are atoms of spin 1/2. If you look at the Schrödinger evolution of a silver atom that is shot out of a gun and then moves through a magnetic field, then the Schrödinger evolution predicts that the wave function of the silver atom splits into two humps. One hump goes towards an upper detector and another hump moves towards a lower detector. And the humps may have different heights depending on the orientation of the initial spin of the silver atom. Now, in an experiment, this is never seen like that. In an experiment, one of the two detectors will fire. Sometimes the upper one, sometimes the lower one. That's the true stochastic evolution. Quantum mechanics only predicts the probabilities of the event that the upper or the lower detector is firing. And this fact that the evolution is stochastic and only probabilities can be predicted should be a basic feature of a fundamental law of dynamics for the evolution of states of individual systems. Point 2. Schrödinger evolution does not describe propagation of states of individual systems. Well, that of course already appeared in item 1, but I want to make it a little more precise now by considering another experiment. Let's suppose we are able to prepare a pair of silver atoms in an entangled spin singlet state, and with orbital wave functions such that one atom propagates to the left, where it moves through a magnetic field, while the other atom propagates to the right, also moving through a magnetic field. The Schrödinger equation predicts the behavior sketched in picture 1 below. while all experiments reveal events as described in picture 2, or in picture 2 with upper and lower detectors interchanged on the left and on the right, and these events exhibit correlations between what is measured on the left and what is measured on the right. Of course, everybody knows that, and the question is, can this be described by some kind of Schrödinger evolution? Let's suppose we do an ambitious Schrödinger evolution where everything in this picture, including the detectors, the magnets, and so on, is included in a Schrödinger evolution. Well, it turns out if the Schrödinger evolution described what we see in picture 2, the conclusion would be actually that what you see on the left does not bias the outcome of what you see on the right. This is a theorem, and it was actually proven in a paper I published with two of my friends in 2015. Well, this apparently does not describe the correct correlations between the events on the left and on the right. And so the conclusion is the Schrödinger evolution is not able to describe the evolution of states of individual systems when they are subjected to measurements. Another related Gedankenexperiment leading to the same conclusion in item 2, namely that Schrödinger evolution is inappropriate, is Wigner's Fremd paradox. Wigner suffered a lot from having discovered that paradox, and he was totally unhappy about the state of affairs, which I guess Erhard and I noticed when we were at Princeton. I should now say that, what you see in picture 2 here, these correlations are usually called the non-locality of quantum mechanics. There is a lot of confusion between this type of non-locality of quantum mechanics and Einstein causality, and there have been many people who thought that there was some kind of tension between quantum mechanics and relativity theory. I think this is entirely misguided. But the discussion has, started early. For example, there is an exchange of letters between Wolfgang Pauli and Reichenbach, where they discuss this problem. But I think there is no problem. And so I'm not going to go into details about that. Maybe when you have questions, we try to answer them. All right. Now, item 3 was about events, potential events, and actual events. Let's look at the example of the double slit experiment. In the upper picture, I have two cavities that are completely dark. On the left, there is a gun that shoots out electrons, for example. And then on the very right, there is a green screen where an interference pattern may show up. If both cavities are dark, then you get the expected interference pattern, which can be, experimentally verified. Every single electron will, of course, hit the specific little region on the green screen, but when you repeat the experiments many times, then you see the interference pattern. If you now illuminate, for example, the cavity on the right with a laser lamp that in fact serves to measure the position of the electron shortly after it enters the right cavity, then the interference pattern will gradually disappear depending on the intensity of the lamp. In the upper situation, where there is an interference pattern appearing, the question whether the particle went through the U slit or the D slit before hitting the green screen is meaningless, for it is a question that does not concern an event that could ever happen. In quantum mechanics, the picture of a particle being point-like and always having a more or less precise position is simply wrong. So the lower picture is about the measurement to the right of the double slit of the approximate position of the particle by light scattering, and then the interference pattern disappears. All right, so this shows that, we can ask about certain events that are not events in quantum mechanics, and therefore the notion of potential and actual events has to be clarified. Finally, about the dichotomy between past and future and the notion of states. These were items 3.2 and point 3. Here's a little picture. You see already in classical relativistic theories that the future is not predictable. And in classical theories, this is because we do not have full access to initial conditions. In quantum theory, it's more fundamental. The future is simply not predictable, while the past is factual. In principle, we could try to record just about all the events that happen, and then the past would be entirely factual. That's, of course, not realistic. Nevertheless, we tend to think that the past is factual. You cannot, it doesn't change anymore once it is past. This dichotomy should be represented properly in quantum mechanics, and it will lead, if properly incorporated, to a fundamental arrow of time, as I will try to explain. The role of states is to serve to predict the likelihood of potential events actualizing in the future. So, for example, here you see a bomb exploding outside my past light cone. It might create a lot of hubris and it might kill me in the next 10 minutes. Of course, I hope it's not going to happen, because then I could not finish the talk, but it cannot be excluded. All right. So this is that was a general introduction to some of the problems that we encounter when we try to find the correct law of evolution in quantum mechanics. Now I will sketch something that I already talked about in my last talk in the series, namely the ETH approach to quantum mechanics. In quantum mechanics, the time evolution of ensemble states, namely of averages of states taken over a large ensemble of identically prepared systems, is usually taken to be linear and deterministic. It's the Schrödinger von Neumann or Lindblad type evolution. I'm not going to change this. However, the quantum mechanical time evolution, as we just saw, of states of an individual system is nonlinear and stochastic. The conceptual explanation of this fundamental fact is the core of the ETH approach to quantum mechanics, a special case of which appropriate for a precise formulation of non-relativistic quantum mechanics is now sketched. Point A, physical quantities of a system S are represented by certain abstract self-adjoint linear operators belonging to a certain family. At every time t, all the elements in this family are represented by concrete operators x of t acting on a Hilbert space. In the Heisenberg picture, the t-dependence of these operators x of t is given by the well-known Heisenberg equations. I introduce algebras of potential events as follows. E greater or equal to t is the algebra generated by all operators x of t prime, where x of t prime represents a physical quantity x hat at time t prime, and time t prime is greater or equal to time t. And then I close the algebra, I define it this way so as to have what people call a von Neumann algebra. Obviously, e greater or equal to t prime is contained in or equal to e greater or equal to t whenever time t prime is larger than t. And all these algebras are unitarily conjugated to one another by the propagator of the system, which is generated by the Hamiltonian H sub s of the system. I assume for simplicity that the system is autonomous. So in particular, all the algebras e greater or equal to t are isomorphic to the algebra e greater or equal to t equals 0. What are potential events? A potential event in quantum mechanics possibly happening at some time greater or equal to t is given by a partition of unity by disjoint orthogonal projections belonging to the algebra e greater or equal to t. So pi sub psi is one of these projections. It belongs to E greater or equal to t, and this X is an index set. That's the right notion of potential events for the purposes of this lecture. What are states? A state of a system at time S is defined to be a normalized positive linear functional on the algebra E greater or equal to t. If and only if E greater or equal to t is independent of time t, as is the case for closed systems or for relativistic systems with a strictly positive mass gap, then in the Heisenberg picture, states are independent of t, obviously. Now I want to formulate certain postulates that are appropriate to try to complete non-relativistic quantum mechanics. The first postulate is what I call the principle of diminishing or declining potentialities. An isolated but open system S, namely a system which doesn't really interact with the rest of the universe, but which can release information to the outside world, is characterized by the property that these algebras E greater or equal to t sit properly inside one another, as described in this property 2. In QED, this property, this principle of diminishing potentiality, is a consequence of Huygens's principle, really of the fact that photons are massless particles, as was proven in a sort of fairly general axiomatic setting by Detlef Buchholz. If this principle holds, then states will generally depend non-trivially on time t, which is a consequence of entanglement, namely of the fact that these algebras shrink as time increases. Principle 2, it's the type 1 property. This is a special principle only appropriate for non-relativistic quantum mechanics. And it says the algebra E greater or equal to 0 is isomorphic to the algebra of bounded operators on a Hilbert space H naught that sits inside the Hilbert space H of the system. This principle immediately implies that the state on the algebra E greater or equal to 0 is given by a density matrix rho naught acting on H naught. And because all the algebras are isomorphic, it also implies that the state of the system at some arbitrary time t is given by a density matrix on H naught. Suppose ES is a large ensemble of systems, all isomorphic to S. Let rho naught be the state of all the systems in the ensemble at an initial time t naught, which I can set to 0. Then the average rho sub t over the ensemble of the states of these systems at the later time t, which is called an ensemble state, is given by restricting the initial state rho naught to the algebra E greater or equal to t, as it is formulated in this equation 3. When formulated with precision, this equation implies that the ensemble state rho at time t can be obtained from the initial condition rho naught by applying e to the tl, where L is a Limplot generator. That means that this semigroup e to the tl, t greater or equal to 0, is a semigroup of completely positive linear maps that describes the evolution of ensemble states. Principle 3 is the state reduction postulate. At all times t positive, the state of an individual system in the ensemble satisfying postulates P1 and P2 is given by a finite rank orthogonal projection pi sub t that belongs to a potential event E in this algebra E greater or equal to t. And this event apparently actualizes at time t. Pi t is a random object. It can be obtained by purifying or unraveling the evolution, the Limblad evolution of ensemble states described in equation 4 above. And since it's a random object, it should have a probability of being encountered, and this probability is predicted by a generalized Born rule. This state reduction postulate is a little tricky, and I will not say more about it, but it will be made precise in the context of specific examples in section 5. The new element of the ETH approach to quantum mechanics as compared to textbook quantum mechanics are ingredient D, namely the notion of states that I've introduced, and postulates P1 and P3. P2 is a little special, and I'm not going to emphasize it anymore. And these postulates have far-reaching consequences. For example, they can be used to solve the infamous measurement problem, which I think is a no problem, or the information paradox and other enigmatic puzzles of quantum mechanics. This concludes part 1, and I now encourage the audience to ask a few questions before we enter the more technical part of this presentation. I just realized that I'm a little behind schedule.
It's fine, I think. Perfect. Half an hour, almost in time. So if anybody has questions to this general introduction, please, you can go ahead and ask now before we enter the specialized talk.
Yes. And of course, if you still want to think about what you heard and you don't have your questions ready, you can ask them at the end of the talk or submit them in the chat or so.
Sure. Okay, so Dirk.
Dirk has a question. Yes, Dirk. Go ahead.
One immediate question here, but I don't know if we should not wait for the more technical talk to answer it. So I think the one, if you go back 1 or 2 slides, please. Yeah, here, where you write under P3, at all times t bigger than 0, the state of an individual system is given by these finite rank orthogonal projections. Yeah.
Yes.
So the potential event was basically the partition of unity by these orthogonal projections. That could be, for example, as it's done for the position operator, as it's done for, or maybe even a discrete thing like spin or something like that. Yeah.
Sure.
But how can I imagine this? Is somehow continuously in time, basically one family of finite rank orthogonal projections chosen, so that I really cannot think of it as a unraveling of the stochastic process in terms of these finite rank projections.
Yes. So I will, make this. I think in the last talk I tried to sketch how P3 can be thought of and be made a little more precise than what you read here. But I decided for this talk I would like to make this precise on an example, because then it's a little easier to understand. And this will be discussed in section 5. The point is, the ETH approach predicts which potential events actualize at the given time, if you know the initial condition and then follow. Then you can predict which potential event actualize, and then a potential event is a partition of unity, and then you have to pick one of the projections in this partition of unity sort of by chance, but the probability for picking a specific projection is predicted by a Born rule. This is, conceptually maybe a little hard to swallow, and I would propose for people who have difficulties understanding what this means, it's maybe better to wait till I've discussed section 5, and then we can go into more detail.
Okay, thank you.
Is that okay?
Yeah, sure.
I remember when I prepared my last talk, Dirk was insisting that I should be more clear about the state reduction postulate. And I tried to do my best, but if I had now gone into more details, I would have gone over time for this general introduction, and I didn't want to do it. So let's wait till section 5.
Okay, that's fine. Maybe a very quick question. These kind of what you call postulates.
Yes.
It's basically something that with a, let's say, an example at hand, we would have to prove. Yeah, it's not something that you put on top somehow on the mathematical structure of quantum mechanics, but it's these are properties somehow that are
Yeah.
defined and then proven to be well defined. Yeah?
Yes. So
Okay.
it turns out, the principle or postulate 1, the principle of diminishing potentialities, is actually a principle I just guessed. I sort of sucked it out of my fingers in order to get rid of all these measurement problems and all this nonsense. But then after a while, and also upon discussing this with Detlef Buchholz, I understood that in QED it is a general fact of life. There are people who don't believe it, but they usually come up with counterexamples that I can demolish. I would love to say more about how this principle can be proven or derived in the framework of specific theories, but that goes a little beyond the scope of this talk. You will see that in the caricature of QED that I will present in part 2, it follows easily. P2 is specific to non-relativistic quantum mechanics. In fact, in a relativistic theory, these algebras E greater or equal to T tend to be what is called type 3 for Neumann algebras, possibly type 2. And then things become a little more complicated because then events can have continuous spectrum, and this leads to certain complications that I will not enter in today's talk. I just see that I had 3 apostrophes rather than only 2 in P2. All right, the state reduction postulate, I think, I will try to explain why this is a natural postulate first on the example of random walk. And then once you have understood that, I think you will buy how it works in quantum mechanics. So,
Okay.
but all these things can really be, in the context of specific models, these postulates can be proven as lemmas or theorems and look entirely reasonable.
I see. Yeah, thank you.
Okay, thanks. So we have 2 more questions. Let's have them before we start the specialized part.
All right.
So Mike,
I don't hear
that is
anything.
gone.
Yes.
So then
Yeah.
Fabian,
Do you hear me?
Yeah. Yeah,
Can you hear
now.
me?
Yes, we.
Yes, thank you. First of all, thanks for the general introduction to this theory. One thing I don't understand is also like with regards to the slide. So for me, the measurement problem is really about like 2 different mechanisms of evolution, right? So on one hand, you have unitary evolution, and on the other hand, you have reduction,
Yes.
basically via projection.
Right.
And now here you introduce another projection postulate to me, like somehow that doesn't really square, like because again you get that, right?
The state reduction postulate is a postulate that has nothing to do with measurements. It is at work all the time, as you will see in section 5.
Right. Well, then I wait.
So
Thank you.
you see the idea that there are 2 types of evolution, unitary and then projection when you do a measurement, I think is an absurd idea because the measurement equipment can also be described quantum mechanically. Of course, it's large systems with many degrees of freedom, And so it may be complicated, but it cannot be that all of a sudden a certain evolution is replaced by another one. This was a good heuristic idea at the time when people didn't have the mathematical sophistication to do better. But by now, we should get rid of this nonsense and find an evolution that is at work, no matter whether there is a measurement equipment around or not. It will work all the time, as I will try to show.
Yeah.
In fact, it's
I
all
was just wondering, I just wonder, like, if you say you get rid of unitary evolution, then how can you get stationary states, for instance? But maybe that's going a bit far.
well, it will turn out that, for example, take an atom, an excited atom, far away from other equipment. It will always relax, well, at least if you neglect the cosmic microwave background, it will always relax into the ground state. And that will be a consequence of the postulates P1 up to P3. So there are stationary states.
Yeah, I think it's going a bit deep now. Thank you, though.
Okay, so maybe we come back to that afterwards.
Yeah, right.
Okay, so we have one more question by Fabian.
Yes, hi. I want to understand if I got the idea of the PDP right. So can I understand it like you have a state of your system, and as time progresses, there are degrees of freedom in your state which are not anymore accessible, and that's by the nature of the interaction, which you call Huygens principle, right? And then
Huygens principle.
yes.
Yeah.
And then you use these coming 3 degrees of freedom for this specific observer, which cannot access them anymore, from time step to time step to build your reduction principle. Is that the correct picture to view it like that?
Absolutely. I mean, the state reduction property would be a trivial property if PDP were violated, if all the algebras would be the same. Then the state reduction doesn't happen. Evolution would be unitary evolution. But thanks to PDP, state reduction has non-trivial content and will predict an evolution that is not described by Schrödinger.
So it's all about the nature of the interaction, which
Absolutely.
makes it so that you have degrees of freedoms which are not anymore accessible
Yes.
to.
I think it's wrong to talk about degrees of freedom. The degrees of freedom are always the same. Think of classical mechanics. PDP in classical mechanics would be the property that certain systems move into a certain subset of phase space and never get out of that anymore, which can actually happen in classical mechanics too. At least as soon as you feel a little bit of friction, it will happen. You see, to some extent, PDP has something to do with quantum friction, and that is why the electromagnetic field will be absolutely important. In fact, I claim that you cannot solve the measurement problem or the unitarity paradox but if you neglect the electromagnetic field.
Okay, all right, thank you.
Okay, thank you very much. So I think we can start with the second part of the talk now.
Very good. Let's start. So let me introduce the systems I want to discuss in somewhat more detail today. I will consider systems consisting of a static atom. I will neglect the orbital motion. But, all these simplifications are just in the interest of finishing the talk around 6 o'clock. You could be more ambitious. Anyway, I will neglect the orbital motion. And the atom has a certain number n of internal states of given energies, E naught up to En minus 1. And these states are given by a complete orthonormal system of vectors in the Hilbert space Cn of the system. And the energies are, of course, the eigenvalues of the atomic Hamiltonian on the eigenstates psi j. The atom will be coupled to the quantized electromagnetic field. And the idea is as follows. It's sort of textbook material. Given two levels of the atom, I and J, one specifies or calculates, if one is more ambitious, a transition amplitude, d sub I j, for a transition from state psi I to state psi j. And these transitions are accompanied by the emission of a photon if energy EI is larger than energy EJ. The frequency is roughly given by what Bohr already wanted it to be, and is accompanied by absorption of a photon if energy EI is smaller than energy EJ. The state space of the photons is the usual Fock space. In textbooks, the dynamics of the atom coupled to the quantized radiation field is described by unitary evolution on the Hilbert space H, which is the tensor product of the atomic Hilbert space and the Fock space. And this time evolution is generated by a Hamiltonian that looks as follows. It's a sum of the atomic Hamiltonian plus the field Hamiltonian plus an interaction term, which I denote by H sub I of Dij. It's completely determined by these transition matrix elements Dij, and it is multiplied by a coupling constant E, which is simply the elementary electric charge. And so, of course, this interaction term describes transitions between the atomic levels accompanied by either the creation or annihilation of a photon. In a non-relativistic regime, where the velocity of light c tends to infinity, this model fits absolutely perfectly into the formalism that I just developed in the last section. The algebras E greater or equal to t that I introduced, which are generated by these potential events happening at times greater or equal to t, these algebras are isomorphic to the algebras of bounded operators on the tensor product of the atomic Hilbert space and a certain subspace of Fock space, which is obtained by applying arbitrary electromagnetic field operators localized at times greater or equal to t to the vacuum. That this is a subspace would even be true in the relativistic theory, but in this limiting theory where the velocity of light tends to infinity, it's a sort of obvious thing that these f sub greater than t spaces are proper subspaces of the Fock space. And therefore we immediately find, and they are in fact nested into one another as you vary time t. So it is essentially a triviality to show in this caricature of QED that the principle of diminishing potentialities holds. For simplicity, just in this talk, for simplicity, I want to suppose that at an initial time, the system is prepared in a state without any photons. That means that the radiation field is in its so-called vacuum state. In the limit, when the velocity of light tends to infinity, the state of the system restricted to the algebra E greater or equal to t is then always given by the tensor product of an atomic density matrix omega t with the projection onto the vacuum of all field configurations that are encountered at times greater or equal to t. And this is true for all times t. The reason is, of course, very simple. If the velocity of light is infinite, any photon emitted at some time smaller than t will already have escaped to spatial infinity at time t. So you will again see. This fact allows us to entirely neglect the degrees of freedom of the radiation field, provided it has been prepared in its vacuum state at the initial time. I could treat other initial states for the radiation field, but then the talk would last a little too long. It has all been described already papers that you find in journals or on the archive. So, suppose omega naught is the density matrix describing the initial state of the atom at some initial time T naught equal to 0. Then the ensemble state of S at time T obtained by restricting the initial state rho naught to the algebra E greater or equal to T is given by a density matrix rho T, which is the tensor product of an atomic density matrix omega sub T times the projection onto the vacuum of the electromagnetic field. As mentioned in the past section, the evolution operator for omega T is given by a Limplatt equation. You know that the tensor factor talking to the electromagnetic field doesn't have to be evolved because it's always in the vacuum. So the Limplatt equation for the atomic density matrix has the form omega dot T equals a Limpladian applied to omega T. The Limpladian has a conventional term, a first term, which describes unitary evolution, and then there is a dissipative term, which is on the right of equation 5, and it is prefaced by a constant alpha, which is simply the square of the elementary electric charge. This evolution, if you don't want to use general theorems, you can just derive it from the model, the way I introduced it. It comes out like this. And that's not a difficult matter. You can use all the results due to Hudson and Baltasarati and people like that, and they yield this equation 5. The operators Vk that appear in 5 are calculated from the transition amplitudes and from form factors of photon creation and annihilation operators that appear in the interaction Hamiltonian. Purifying or unraveling this equation 5, this Limplatt equation, will yield the non-linear law of the stochastic dynamics of individual quantum systems isomorphic to the system S. And this law will be given by what I like to call a quantum Poisson jump process. It will be described in detail in section 5. Unraveling involves interpreting the spectral projections of a density matrix describing an ensemble state at time t as an event actualizing at time t. Now I want to explain that on the simpler example of random walks on a lattice. So let's consider a large ensemble of identical, non-interacting random walkers on the simple lattice Z nu. Nu is the dimension. An ensemble state at time t is simply given by the density rho sub t of random walkers on the lattice. The time dependence of rho t is governed by the diffusion equation, namely the equation rho dot of t at the point x is equal to a diffusion constant d times the discrete Laplacian applied to rho t evaluated at x, which of course is by the definition of the discrete Laplacian is given by the right-hand side of 6. The sides y over which you have to sum are nearest neighbors of x. All right. The diffusion equation in 6 is a linear deterministic evolution equation, just like the Schrödinger equation is a linear deterministic evolution equation. And it tells us how the ensemble state rho sub t moves in time. It is the analog, as I said, of the Schrödinger or of the Limplatt equation. The solution rho sub t is non-negative for all times t, provided rho naught is non-negative, a consequence of the fact that the Higgs kernel is positivity preserving. This is the analog of the fact that the Limplatt evolution consists of completely positive maps. Furthermore, the total mass of a density rho sub t is always independent of time t. These are exercises which I propose to the audience to be solved during dinner time. So we can normalize rho t such that its total mass is 1 for all times t. We would like to understand what kind of stochastic motion of a single random walk omega in this ensemble implies that the time-dependent state rho t is given by the diffusion equation. For this purpose, we have to unravel the diffusion equation. It helps the intuition to rewrite in the following form. Rho sub t plus dt, where dt is the time increment, is equal to rho t plus diffusion constant times Laplacian applied to rho t times dt plus further terms of order dt squared. And of course, dt will be assumed to be extremely small, so the further terms don't have to be made explicit. What's the ontology of this system? The true state of an individual random walker omega in the ensemble at an arbitrary time t is a site x sub omega of t in the lattice set nu, which corresponds to pure state given by a Kronecker delta sitting at the site x sub omega of t, which of course here plays the role of a pure state. During a time interval from time t to time t plus dt, a random walker omega may remain at the site x sub omega of t where it arrived at time t, or it may jump to a nearest neighbor site y. That means that its state may jump from the pure state delta sub x omega t to a state delta sub y, where y is the nearest neighbor of x sub omega of t. The equation 7 determines the probabilities for this random walks to remain at x sub omega of t or to jump to a nearest neighbor site. For this purpose, I just introduce again into equation 7 the definition of the discrete Laplacian. Then it looks like that. And the coefficient rho t plus dt is a coefficient given by 1 minus twice the diffusion constant times dimension times dt times rho t plus terms that describe states that are obtained by making nearest neighbor jumps. They all have coefficients of order dt. All right. So that means that apparently the state at time t plus dt, it's an ensemble state as predicted by the diffusion equation, is a convex superposition of pure states corresponding to the site x sub omega of t or to a site x sub omega of t plus delta, where delta ranges over all nearest neighbor jumps. The coefficients appearing in this superposition can be interpreted as probabilities. If dt is tiny, rho t plus dt is given by either the pure state at the site x sub omega of t with a probability that I call p sub no jump, that is given by 1 minus twice the dimension times the diffusion constant times dt, or by a pure state at the neighboring site with a probability given by diffusion constant times dt. All right. Probability that there are two jumps in a short time interval from t to t plus dt is always order dt squared. So it will such multiple jump probabilities disappear when you let dt tend to 0. As you see from equation 8, the sum of the probability of not doing a jump plus the probabilities of doing a nearest neighbor jump add up to 1. From the top equation in equation 8, you immediately find out that the probability of not doing a jump between times t prime and t double prime is exponentially small. It's given by e to minus 2, the dimension, twice the dimension times the diffusion constant times t double prime minus t prime. Suppose now that x of omega of tau is the position of a random walker starting at time tau equals 0 at an arbitrary site omega naught in the lattice and making little n equals length of the random walk omega jumps along a given simple random walk omega. And these jumps are supposed to appear in time intervals between time tk and time tk plus tk, where k runs from 1 to n. And then finally, the random walk will be stopped at some time t. By using equation 8, we can compute the probability of encountering such a history among random walkers. And it is given by a probability density W sub omega that depends on the times when the jumps appear, T1 up to Tn, times the product of the time increments dTj. And by just using equation 8, you find the middle expression for this probability, and then when you compute it, it turns out it's given by either minus twice the dimension times diffusion constant times the final time t, the stopping time, times the product of the time increments dt1, dt2, etc., up to dtn. So this is, of course, a Poisson jump process. Everybody knows it. And using this expression for the probability density, you can calculate, so to say, all elementary properties of simple random walks. So, for example, it's very easy to use this expression to compute the mean square distance a random walker travels in time t. I did the calculation here on the top two lines of the slide. Turns out it is twice the dimension times diffusion constant times t. So it grows linearly in time t, as of course everybody knows. So this can all be derived. In any event, we have seen how to pass from the diffusion equation for the evolution of ensemble states to a stochastic process that tells us how individual random walkers move in time. I'm going to do something similar, but for quantum mechanics. So this is section 5, and section 5 is in some sense really the most important section of this lecture. So we consider a system isomorphic to S, as I specified in section 3, namely, say, an atom with finitely many internal levels coupled to the radiation field in this limiting regime where the speed of light tends to infinity. We prepare the system at time t naught equals 0 in a atomic state omega naught, tensored with the projection onto the vacuum of the radiation field. You may assume that omega naught is a pure state. That would mean that it's given by a rank 1 orthogonal projection pi naught. All right, so
Jürg,
there are no detectors recording. Pardon?
Jürg,
Yes. What?
sometimes, I mean, during the last
Yes.
couple of minutes, the connection seems to drop a little bit. I think it's still completely okay to understand you, but
In my computer, the Wi-Fi is completely black, so I hope it's not going to be a problem. Otherwise, you tell me, then I can repeat something.
okay. Yeah, I think at the moment it's still okay. Also, the slides are very comprehensive, so I think we can follow. But if a bigger dropout happens, then I'll or Paula will.
Yeah, I hope it's not going to happen anymore.
Okay. Thank you. Yeah, okay, let's continue.
All right. So, so you see, as I said in section 3, the evolution of the atomic state is given by a Lindblad evolution. You saw that the Lindblad evolution would be unitary evolution if the coupling of the atom to the radiation field were turned off, namely if this constant alpha that you see in equation 9 were equal to 0. So we already see apparently dissipation, Strahlungsdämpfung of atomic processes appear because the atomic degrees of freedom are coupled to the electromagnetic field. This would even be true if I did a relative, but then I couldn't do many computations because it becomes too complicated. I assume for the purposes of this lecture that there are no detectors that record the photons that are emitted. I could do another talk where the photons that are emitted are recorded, and then, you know, the unraveling of the Limblad evolution would look a little differently. So, but let's just do this one case where emitted photons simply disappear before they can be recorded. According to the ETH approach, the state of an individual system isomorphic to this atomic system is then given by a projection pi sub t, tensor projection on the vacuum. And what we have to find out is how this projection pi t evolves as a function of time t. And that should follow from the principle of diminishing potentialities and from the state reduction postulate that I reviewed in section 2. So let's see how that goes on this particular example. So let's assume pi t, the state of the system at some type t, happens to be a pure state, namely that pi t is a rank 1 orthogonal projection. I could do it for higher rank projections, but then formulas become a little more complicated, so let's not. Then the state at time t plus dt, when averaged over a large ensemble of systems, all prepared in the same pure state, pi sub t tensored with the projection onto the vacuum of the radiation field, is then given at time t plus dt by a certain density matrix. It's a density matrix because Limblad evolution preserves the property of being a density matrix. So this density matrix is called omega sub t plus dt, and it is given by the state at time t, which is this projection pi sub t, plus the Limbladian applied to pi sub t times dt, plus correction terms of order dt squared. The state omega sub t plus dt is not pure anymore, since it is density matrices are self-adjoint. I can use the spectral theorem to decompose omega t plus dt into a convex combination of disjoint orthogonal projections. And that's given in section 11. Omega t plus dt is a projection pi mod sub t plus dt, which is probably close to pi sub t because it belongs to the largest eigenvalue p sub node jump that is close to 1. And then there are further projections that have small eigenvalues, small probabilities of being encountered, that are denoted by p delta. Delta runs from 1 to n minus 1. N is the dimension of the Hilbert space, as you might remember. And these projections might not all be rank 1, so you want to normalize them so as to be states. And as I said, the probabilities p delta for delta larger or equal to 1 are of the order of dt of the time step. Again, simply because the trace of a density matrix is unity, the sum of these eigenvalues or coefficients p sub n, the sum over delta equals 1. Of course, nj stands for node jump. According to the state reduction postulate of the ETH approach, one of the operators pi hat delta randomly chosen is the state of an individual atom at time t plus dt. Pi hat super naught is simply the one where there is no big jump happening. So the way these dictated the probability or frequency that the path delta sub t plus dt is chosen is given by the coefficient p super delta. In order to come up with explicit expressions for these quantities, I have to make a little digression on what I call infinitesimal analytic perturbation theory. It's a form of perturbation theory that should be in all the books, for example, in Reed and Simon, volume 7, but it's not. So I have to briefly explain it. So what is infinitesimal perturbation theory? Suppose H naught is an operator on the atomic Hilbert space Cn with a simple eigenvalue E naught, separated from the rest of its spectrum by a strictly positive gap. Let us denote by pi the projection onto the eigenstate corresponding to E naught. Suppose V is an operator on Cn that perturbs the Hamiltonian H naught. Then I introduce a Hamiltonian H of epsilon, which is H naught plus epsilon times the perturbing operator V. In our application, epsilon will be the time increment dt, so it will be very small. We are interested in formulas for the perturbed eigenvalue E naught of epsilon of H epsilon, and also for the eigenprojection onto the eigenvector of H epsilon corresponding to the perturbed eigenvalue E naught epsilon. Well, of course, these formulas are well known. You find the projection pi epsilon by a unitary conjugation of pi with an operator S that is well known to everybody. I called the formula in equation 12. And the perturbed eigenvalue is given up to order epsilon simply by what people call the Feynman-Hellman theorem, which of course is probably really Schrödinger theorem. I'm sure Schrödinger knew it. Namely, E naught of epsilon is the unperturbed eigenvalue plus epsilon times the expectation of the perturbation in the unperturbed eigenstate up to terms of order epsilon squared. And pi epsilon is simply the conjugation of pi by this operator S computed up to order epsilon with error terms of order epsilon squared. Up to errors of order epsilon squared, the remaining eigenvalues of H epsilon can be found by diagonalizing the matrix pi perp. Pi perp is 1 minus pi times H epsilon times pi perp. All right. If you want to diagonalize an operator H1, knowing the spectrum H naught, it is a good idea to connect H naught to H1 by a family of operators H sub t. The parameter t runs between 0 and 1. And you should pick a family, an interpolating family that is differentiable, and then you can actually find the spectrum and the eigenstates of all the operators ht for t between 0 and 1 by solving an initial value problem consisting of a system of ordinary differential equations derived from formulae 13. This is a useful variant of perturbation theory. I call it infinitesimal perturbation theory because it works in where analytic theory breaks down, for example, because of eigenvalue crossings. I will not go into further mathematical details of this, but it's definitely a form of perturbation theory that deserves to be reported in all the books. Unfortunately, I don't write books, so I might never enter the books. So let's apply this infinitesimal perturbation theory to derive from the Limblad equation 10. I recall what it was. Here is the Limblad equation 10. A system of ordinary differential equations for the states pi hat naught of t, which is the state, pure state at time t of the system in the absence of a quantum jump. In other words, I never choose these jump states, but I always choose the state that belongs to the largest eigenvalue. So I claim these states can be found by, this leads to a system of ordinary differential equations. H naught is the unperturbed state of the system pi sub t. The perturbation is the Lindbladian applied to pi sub t, and the coupling constant epsilon is the time increment dt. Apparently, the spectrum of H naught is simply given by an eigenvalue of 1, which is simple because I've assumed pi t is a one projection by m minus 1 folded by the formulas I had on the previous slide, 12 and 13. Then apparently the S operator is given by the expression here that you see in equation 14. It's a well-defined anti-symmetric matrix on Cn. And in the perturbation theory, the probability not to make a jump, namely to choose the state pi hat naught sub t, is given by 1 plus trace of the perturbation in the unperturbed eigenstate times the coupling constant, which is dt, up to errors of order dt squared. That's Feynman-Hellman. If you take the logarithm of this equation, divide by dt, you find it's given by trace of pi t times L alpha applied to pi t, which is easily shown is 0. So we find the probability of not between 0 and the time t, or to t, trace pi sub s times L sub alpha applied to pi sub s ds. And this is always smaller than 1, smaller or equal to 1. All right.
Jürg, may I stop you once more? Because we still have some dropouts. So I think Paula and I will also turn the video share off. Yeah, and I hope that increases a little bit the bandwidth. So I think we can still understand you okay, but maybe that will help. I just wanted to tell you before we just switch it off.
All right.
And I hope that this increases a little bit the performance.
I'm sorry about this problem. I don't know, maybe there are too many people using, but you see the Wi-Fi seems to work fine at my end. I don't know what the problem is.
Okay. Now, I mean, we switched out completely the video shares, so we're still there. We can hear you,
All right.
but we don't share the video anymore. I hope this improves the performance. I'm sorry for the interruption.
Yes. So this was how to calculate the no-jump probability. How do we calculate the time dependence of the state of the system in the absence of quantum jumps? Namely these projections pi sub t. Well, by the infinitesimal perturbation theory tells us that the time derivative of pi sub t is given by pi t perp, which is 1 minus pi t, times L alpha applied to pi t times pi t plus summation conjugate. This is a system of nonlinear cubic differential equations for these projections pi sub t. I think a similar equation has appeared first in a paper of Dichotomy many years ago, but he might comment on that in the question session if he's still listening. I tend to think that maybe the equations appeared for somewhat the wrong reasons. And I'm not quite sure that the probabilities, these no jump and jump probabilities, were ever calculated in detail. In any event, here they are calculated. What about quantum jumps? if the system decides to make a quantum jump, we have to diagonalize pi perp sub t times L alpha pi t times pi perp of t. The eigenvalues are given by these jump probabilities p delta divided by dt. They can be computed by explicitly diagonalizing this explicit matrix pi t perp times L alpha pi t times pi t perp. All right? So you find that these jump probabilities are order dt. And you also find, just by looking at the expression for p no jump and for p delta, that the probabilities of p no jump plus some delta from 1 to n minus 1 p delta equals 1. So the probabilities add up to 1 as they should. If the fine structure constant were 0, namely if the atom were decoupled from the radiation field, our evolution would reduce to ordinary Schrödinger von Neumann evolution. The probability not to make a quantum jump would be identically equal to 1, and the time dependence of the projection pi sub t onto the state of the system at time t would, the time dependence would be governed by the usual Schrödinger von Neumann evolution, as we might expect. So apparently you see that in this example, you see very clearly that the only reason quantum systems apparently tend to make jumps occasionally is because the systems are coupled to the radiation field. And if the radiation field were strictly massive, there would be no jumps. But since photons are massless, there can be jumps. Now you can introduce an analog of the Wiener or the Poisson measure that I discussed in the last section for random walks. Suppose the system exhibits quantum jumps at times t1 up to tn before I stop its recording at some time t final. The state evolves continuously between jumps, between quantum jumps at times tj and tj plus 1, according to the differential equation that I just derived on the last slide, namely this equation in point 2 on top of this slide. This projection is denoted by pi sub t delta j minus 1. And it is the true state of the system for times between tj and tj plus 1. And t naught, of course, is 0. Pi upper delta naught delta minus 1 at time t equals 0 is the initial state of the system. We would like to calculate the probability of encountering a trajectory Tn of states of this type that I have described, where the jumps appear in time intervals between time tj and time tj plus dtj, where j runs from 0 to n. Well, this can be computed, and let's not go into too many details. It's from what I said so far, it's very easy to complete this computation, and you find that this probability is given by probability density that depends on how the system jumps. These jumps are indexed by delta 1 up to delta n. They appear at times t1 up to tn, and the time increments have to be multiplied. The dtj's are multiplied from j equals 1 to n, and then you plug in the probabilities for not making a jump and the probabilities for making a jump, and that is the analog of the Wiener measure of Brownian motion. This formula serves to determine the probability of measurable sets of quantum trajectories of individual systems with an arbitrary number of quantum jumps in the time interval from 0 to t final. This formula has been entirely derived from the basic premises of the ETH approach. I've not used any heuristics, or I've not made any measurements. I've not appealed to von Neumann postulates or nothing. It's a pure consequence of the basic postulates of the ETH approach. Here are two remarks. If an average over the states in the trajectories Tn is taken using these measures W sub Tn, and then varying the number of jumps, then we recover the ensemble states omega sub T that obey the Limplatt equation from which I started. This is very analogous to what happens in the example of diffusion and random walks. Point 2, remark 2, the equation in 2, namely this wonderful nonlinear equation for the evolution of the projection onto the state at time t. This equation can also be reformulated as a certain nonlinear Schrödinger equation for a pure state vector psi sub t, where pi t is simply the projection onto psi t. Since these are nonlinear equations, these equations might actually exhibit chaotic solutions. And I tend to think this will lead to a somewhat different approach to the problem of quantum chaos. Now, this was the end of the introduction. If you have not understood something in the section 5, please record your question and ask it at the end of the talk. Now I may be close to the end of the time slot I have. Is that so? Should I stop within the next 5 minutes? I don't hear anybody.
Yeah, 5 minutes is good.
5 minutes, is that okay? Well,
Yes.
then I will skip much of section 6. Section 6 is a specialization of 5 to a 2-level atom. States of a 2-level atom can be described by vectors on or inside the Bloch sphere, namely by density matrix that are given by 1/2 times the identity 2x2 matrix plus a vector n dot, the vector of the 3 Pauli matrices. And this vector n has a length smaller or equal to 1. If the length of n is 1, then omega sub n is a pure state, and it's given by a rank 1 projection. If n is smaller than 1, it's a density matrix. It's a mixture. If you want to describe the fluorescence of such a 2-level atom, the Limpladian you should choose, at least a simple version of the Limpladian, is given in equation 19. And now we can plug these quantities into our nonlinear equation for the evolution of a state in the absence of quantum jumps. First, I rewrite the Limplatt equation as a differential equation for the vector n of t. Again, it has a term that preserves the length of the vector n of t and simply describes a precession around a certain axis E3, and then there is a term that describes dissipation. And now we can make the sort of moves of the ETH approach and find and unravel this equation 20. And what comes out is a process that describes the motion of n of t starting on the Bloch, on the surface of the Bloch ball, on the Bloch sphere, and then the evolution is described by a certain nonlinear equation for this vector n of t, but every once in a while n of t makes a jump to the antipode. And so there is a flip in the vector n. And the probabilities for continuous evolution and for flips are computed by the tools I developed in the last section, and you get various nice formulas, and then you can find the evolution of n of t and derive the nonlinear equation that arises by unraveling. It can be encoded into an equation for the third component of n of t, and that's the equation 23. It's a nice cubic equation which can be solved by elementary means. And I think since it is getting a little late, not going through the details of the solution is really an exercise. Propose this whole problem level atom treated according to the ETH approach in a course of almost first year students in quantum mechanics, and they would be able to reproduce the formulas on the slides that I'm skipping over. So let's conclude. I have derived very explicit results. Well, maybe I don't talk about two-level atoms, but immediately jump to the conclusion. In idealized models of systems of charged matter interacting with the quantized electron, which I describe in the limiting regime where the speed of light approaches infinity, the principles of the ETH approach or ETH completion of quantum mechanics apparently yield totally explicit predictions concerning the stochastic time evolution of states of individual systems. We don't have to appeal to any, collapse mechanisms or things that are not found in the books. We just have to complete the treatment of quantum mechanics in the books by imposing the three postulates of the ETH approach. And then we get absolutely explicit formulas for the evolution of individual systems in quantum mechanics. These evolutions exhibit periods where there is no jump and the state of the system evolves continuously according to a certain nonlinear equation, and then every once in a while there is a quantum jump to a state that is orthogonal to the incoming state. This is a novel type of stochastic buses. It's some type of Poisson jump buses, but the Poissonian probabilities have to be computed by solving nonlinear equations. As I mentioned before, I think equations of this type first appeared in a paper by Dichotomy in 1988, but I didn't quite understand the concepts that led him to derive these equations. Here, I think the concepts are totally clear. It would be interesting to test the fine print of these predictions in experiments. You see what here goes beyond textbook quantum mechanics is that you could calculate fluctuations of individual systems. Ordinary quantum mechanics just gives you ensemble mean values of what happens. But here you can compute the fluctuations, and some of these fluctuations can be compared with what happened in experiment. For example, if you look at an atom and you subject it to Rabi oscillations, then every once in a while it will spontaneously emit the photon. The emission times are random variables. The formalism I sketched here predicts the law of these random variables, and then you can compare the prediction with what you see in the experiments. And so I think in principle it is possible to test the predictions of the ETH approach in experiments. Let's return to physics. As indicated in this and emphasized in this lecture, fields describing massless photons, if you photons in principle for the dissipative nature of ensemble evolution and for the stochastic nature of the evolution of states of individual systems. If you want to solve the measurement problem without taking into account the electromagnetic field, you will fail. In fact, the entire formalism I sketched here on the example of fluorescence can also be used to describe measurement processes. Of course, then you have to incorporate at least an idealized description of the measurement equipment into your description. This has been actually already sketched in a paper published together with Alessandro Pizzo. But there in that paper, the time increment dt was strictly positive. We discretized time. With the formalism that was sketched in section 5, you could actually extend the results in the paper with Pizzo to models with continuous time. But I cannot possibly do that anymore, otherwise you will starve. You might become very hungry at some point. The methods described in this lecture on the example of the theory of fluorescence of atoms, yeah, that's what I just said, can be used to describe measurement processes. A variant of the ETH-approach applicable to relativistic quantum theory has also been developed. A certain summary of that approach has been published in a paper that appears in a memorial volume for Girardi, and I've also talked about it in various talks. Obviously, I cannot go into it here. Of course, the relativistic case is more tricky, especially since we don't have models of relativistic quantum field theory of which we are sure that they make sense. So there are details that, of course, will have to be understood better. I would like to conclude here, and I thank you for listening. And of course, I'm happy to take your questions.
Thank you very much, Jürg.
Yeah, thank you very much for this very interesting talk. So,
Incidentally, if anybody wants to have the slides, you just send me an email. I can send you the slides.
Yeah, if you like, we could upload it also on our webpage.
Oh, okay, fine.
In the end. So unfortunately, yeah, there were really short but frequent dropouts, and I think it was still good enough that we could really follow through with your talk. I mean, we tried to switch off the videos, but there was not really so much that we could do to mend the problem. So, but I hope that the connection is at least good enough for a little discussion now at the end. So if you have a dropout,
Yes,
then we have to be
about this
patient with each
problem.
other. Okay, Paula.
okay, so anybody who has a question, you can please raise your hand and also turn on the video again so that we can see you. I think we try for that. So,
Very good. Martin has a question.
first question by Martin.
Thanks, Jürg. I understood a lot more today than in previous lectures. You just mentioned Girardi a moment ago.
Yes.
I guess that's Girardi, Rimini, Weber. Is that right?
Absolutely, yes.
GRW.
Yes.
Now, they have a formulation of quantum mechanics which is nonlinear and stochastic. I have forgotten how it works. Can you briefly sort of give us the delineation? So how is their formulation different from the ETH? What's sort of the can you say that in a sentence or two?
Yes, I can say it in a sentence or maybe 5 sentences.
Okay.
GRW introduce a new mechanism into the Schrödinger equation that causes the wave function to collapse or to spike up, for example, in X in position space, that it all of a sudden becomes concentrated in specific locations. To achieve this, they have to introduce a mechanism that is not in quantum mechanics. So it's really a modification of quantum mechanics. And the mechanisms they introduce look to me very much ad hoc. So I didn't want to follow what they are doing. It turns out, if this principle of diminishing potentiality holds, which is the case in QED, you don't need to introduce new mechanisms. You just have to realize that in QED, the evolution of ensemble states defined according to the definition I gave in the talk, this evolution is dissipative, and then if you add the usual state reduction postulate that we're all used to, you have your collapses and you find these non-linear evolution, stochastic evolution equations for the states of individual systems. If you then take an average of the states of large ensembles, the ensemble states evolve according to a Limplatt equation, as you know, an equation that you find in the books when you look under the heading of radiation damping. So I don't have to introduce any new special mechanisms for collapse. It comes out, so to say, automatically from a correct understanding of quantum mechanics.
Okay, thank you.
Okay. So another question by Dirk, please.
Jürg, thank you very much for the nice talk. I think I also understood a bit more now. One question that remains to me, I mean, we looked at these two applications where I think in the first application, we followed the stochastic evolution of somehow the spin degrees of freedom of the atom, or the level degrees of freedom of the atom. And also in the fluorescence application, we looked at the evolution on the Bloch sphere. So somehow it was quite natural that the evolution happens in these degree of freedoms. But if I think further, and I don't mean mathematical difficulties now, really just the physical heuristics. For example, if we take the first application, but take into account also position, so that we have really an atom with orbitals and so on. I mean, the question is my picture correct, that along this trajectory of actually events, so somehow like you described as the potentialities that actually happened, you know? Could it be that every now and then we switch between projectors of the position degrees of freedom and projectors of the spin degrees of freedom? But
no, you should look at the entire projection onto the state. Yes. So you see, when you look at the details, the shape of the electromagnetic field that is emitted will, of course, depend on the approximate position of the atom when the emission happens. And this will automatically, if you go through the sort of grammar of the ETH-approach, this will mean that when an emission happens, the atom jumps to a state that is roughly localized in X space. How well the localization is, that depends on the choice of the interaction Hamiltonian that describes the interaction between the atom and the radiation field. What certainly does not happen is that the atom will be localized in point-like. There are no point-like localizations predicted. In fact, we have written a paper about particle tracks together with Phasen and so on. And there, of course, we didn't do the details of the interaction between the atom and the radiation field. these interactions were put in a sort of effective way, in an idealized way. But then it turned out that, the atoms start to trace out tracks, as you would expect from an atom that, say, goes through a bubble chamber.
Mm-hmm.
In fact, it was explicitly mentioned in that paper that we imagine that the positions of the atom will be, so to say, measured in quotation marks by light scattering.
Okay. Yep.
So, but you see, so to cut it short, this formalism is good enough to describe events where atoms get localized in small regions of space. But if you want to know the details, then that will be another talk.
Yeah. No, it was not about the mathematical details. It was rather about, I mean, there must be a mechanism that somehow decides which partition of unity is let's say, the potentiality that is then turned into an event, right?
But that was talked about.
Okay.
I mean, it would have been simpler to explain this with a discrete time step.
Mm.
But then you heard it in my last talk, and if you didn't understand it then, we should have a Skype or a Zoom discussion where I will explain to you every step.
Okay.
Given a state at time t, it determines which event actualizes at time t plus dt. There is no free choice. It's completely determined. This is why we get these totally explicit evolution equations for the state of India.
I see.
You see, that's a consequence.
Mm-hmm. But could it really be that in time step one, it somehow localizes somewhere in position space? In time step two,
Absolutely.
it is projected to a spin up, for example.
I mean, well, usually the events that happen, if there is a jump, you can jump from a state that is more or less well defined in X space to a state that is well defined in spin space. But normally, as I showed, the evolution of the state is continuous in time, and only at discrete times there is a jump. So yes, it could happen that the state at time t equals 0 is localized in X space, and at time t equals 1, it is localized in spin space. That is possible, but it is a relatively unlikely event. And the probabilities for such jumps have been described in this lecture. And the probability for not making a drastic jump but evolving continuously have also described in this lecture.
Okay. Let me end with a hopefully very short question. Then Peter, I will hand over to you. I mean, for some reason in our experience, position space seems to be very special. Yeah, almost, I would say everything that we interact with in principle can be based on position space information.
So that's the sort of the Bohmian dogma.
Yeah, but
which
CSL is also based on position space, basically. But is there any hint in the ETH approach that somehow localization in space is somewhat special, or I mean, so in order to somehow explain why we live in these three dimensions.
Is a hint which could make relatively explicit because of the special nature of the interaction between particles that couple to electromagnetism and the electromagnetic field. If you look at the details of electromagnetic interactions of charged particles, you will find out that if there's a lot of radiation emitted, for example, because the particle is undergoes an accelerated motion, then the localization in position space will become better and better. But you know, these are, I mean, you cannot talk about all that in one talk. It's
but that's okay.
tracks. You see that this can be understood somewhat. I think the paper on particle tracks will have to be extended by embedding it very properly into the ETH-approach, which we haven't done yet.
Okay, but that's okay. I mean, therefore we have the discussion.
I need young people who get interested in. We need young people who get interested in this material and start to write their own papers, because I'm a very old man. I cannot do all the work by myself. I think Peter Morgan has a question.
Okay, yeah, let's hand over to Peter then.
So I am skeptical of the idea that we must introduce a discrete jump stochastic process. But of course, there are very, very many people who are
I
introducing
have
stochastic
not
process.
introduced it. I have derived it from basic principles.
Right. Well, that
Of this-
I understand that you say that, but it seems to me that when we look at an oscilloscope, and or even if we're just recording the voltage at much faster than gigahertz rates, terahertz rates, whatever speed you want to have your apparatus running at, then what looks like a discrete event starts to look like just a rise time of the signal coming out of a particular device. So that you would just apply ordinary signal analysis to. You discuss what window function you might use, which has an exact analog in quantum field theory of just a test function. The other aspect of this is that I mean, to go back, I very much agree with your focus on electromagnetism, that in many ways we're working in voltage space or in current space when we measure the voltage out of a device that we're using to monitor what's happening within our experiment. So I don't know whether you've had I think I've mostly covered what I put in the chat.
So you see, the fact that there are these sort of somewhat brutal jumps at discrete times is, I think, a consequence that I look at an idealized model of QED where the speed of light tends to infinity. If you had a finite speed of light, these jumps might look a little smoother than in this particular model. The problem is when you have a finite speed of light, you don't have mathematically consistent models unless you discretize the time step, which is what we did in this paper with piezo. But even if you discretize the time, calculations for models with a finite velocity of light tend to be enormously complicated. And I could not have presented any of these very explicit equations. But you might like them, but then, you know, you should try to do the corrections that arise from a finite velocity of light, which I bet is going to be a lot of work.
Right. Okay. Well, I will leave it at that. Thank you.
Okay, so I think it's quite late already, so maybe this would even be a good point to end it here. Dirk, what do you think?
Jakob has another question, I think.
Yes.
Jakob. Yes.
Jakob, please.
Jakob, so then please go ahead.
Okay. First of all, thank you, Jürg, for this really beautiful, comprehensive lecture. I agree totally with Martin Zirnbauer that this, so to say, opened my eyes for something which I had not realized before. But my question is about something different, namely, So what you have talked about concretely is a model where, of course, the electromagnetic interaction is essential. Now, however, there is an interaction in nature which is no system can avoid, and that is the gravitational interaction. Of course, that is extremely weak, as we all know, but nevertheless, it may be not such a completely outlandish question to ask if you think that gravity also plays a role in this, so to say, in this interpretation where where information is carried away with speed of light.
Right. So you see, there are people who always say, well, electromagnetism can be shielded by erecting huge walls, metallic walls at the boundary of our galaxy, and then what happens with my formalism? Now, that's, of course, a nonsense complaint for reasons that I cannot go into. But you could argue that if you want to have an interaction involving mass not be shielded, then of course gravitation
Exactly.
is special in this respect. And you could, I'm sure if you have big masses moving around in experiments, gravitational effects will become important. Of course, Roger Penrose always emphasizes that collapse should be a consequence of gravitational interactions. I tend to think if I look at the phenomenon like fluorescence of atoms, the gravity is not.
No, it would of course be completely
too weak.
Yes,
but,
yes.
But so to cut things short, I think it would be good to try to estimate the importance of gravitational effects, and they are there is beyond any doubt. But I have not computed them, and I tend to think in many earthly experiments, these effects will be so small that we shouldn't worry about it.
Okay, thank you.
It was a pleasure to see many old friends, in particular you, and so on. I hope I hope it was somewhat entertaining.
Yes, it was certainly.
Very good. All right. And Martin has another question. What's your question, Martin? Your microphone is. You want to applaud, maybe.
This was just final applause.
Yeah. So I think this is now a good time to maybe end the question session. So if you want to have the videos larger, maybe you can stop the screen sharing to see everybody again.
Yes.
Otherwise, I would say that this is a good point to stop. And thank you very much again for this very interesting session. I think it was a very nice
Wish you all a very happy end of the year. Let's hope next year will be more peaceful than the present one.
Yes, that we all hope, I guess.
Right. Bye-bye.
All right. Thank you so much, Jürg. It was really a pleasure. I hope this new format also was pleasant, and we continue maybe, I think next year with our next speaker. We'll announce it again on the newsletter and so on, the procedure. Thank you so much for coming, everybody. And hopefully, we talked to each other soon and discuss more about the foundations of quantum mechanics. And Jürg, I'll promise I'll rewatch the last talk.
Very good. Or you give me a call and we will discuss it in person.
I think so. Thanks so much. Yeah, sorry for little disruptions. The connection was not too good, but there was not really
sorry about that.
Yeah. All right, and send our greetings to Eva as well.
Okay, thanks a lot. And goodbye, everybody.
Goodbye. Have a good evening.